Hola amigos, vamos a seguir paso a paso con nuestro trabajo. We're going to continue step by step through this process. We are currently in step 6. These next two videos, this one and the next one, are going to be extensions to step 6 that are actually optional, but give a lot of nuanced understanding that goes behind some of the techniques that we're using in this LANA algorithm. Remember that step 6 was to determine all the ordinary and generalized nodes in our circuit. Remember that we said that a generalized node was any set of circuit nodes connected by a path of voltage sources, so it was actually a set of circuit nodes, whereas an ordinary node was a single node to which no voltage source was connected. When we were actually looking at the circuit, we said that in order to find the generalized and ordinary nodes of our circuit, we're going to use the deactivation circuit heuristic, and that was to deactivate the circuit. Every voltage source we were going to replace with a short circuit, literally just draw a line and pretend it was a wire. Every current source we were going to draw an open circuit, cut out that body, and pretend that the two nodes were not touching at that place. Formally speaking, this step is actually quite quick. If we just deactivated the circuit, we could determine this entire generalized and ordinary node structure quite quickly, but there's a lot going on behind the scenes, and that's what I want to get into now. The first thing we're going to do when we're exploring the foundations behind step 6 is start with our curiosity. One of the things that's quite amazing is this very easy step of deactivating the circuit leads to some very deep ideas. And the question is, why does that deactivation heuristic actually work? What does it give us that's useful? As we tug that thread, as we ask that question to unravel this mystery, the first observation underlying step 6 is that every voltage source in our circuit introduces interdependencies between the node voltage potential variables on each lead of the source. Remember, each source is two terminals, so it has two leads. The moment that I put a voltage source in my circuit, the variables representing the node potentials at each lead are now connected. Formally speaking, that's all that's being said in this table, that entries 2 and 7 in our node potential vector U sub G are connected, and then entries 4 and 5 are connected. And the way that we did that is we literally just looked which of those nodes are connected by a voltage source. The reason that they're connected actually has to do with an algebraic statement, which was what we discussed last time. The voltage drop across each of those voltage sources, which is known, is the difference between these two unknowns. Well, if we have two unknowns and one known, that means that one of those unknowns, as a function of the other unknowns, those are dependent. But the point of linear algebra is not to deal with this information in scalar form, instead translate it into matrix form, and then use the structures of the matrices to say something intelligent about the system as a whole. That's exactly what we do here. Instead of having two scalar equations, we turn it into a single vector equation. And we use our fluency with matrix vector multiplication to recognize that this vector equation actually represents a matrix vector product, where we're saying, hey, take the incidence matrix corresponding to the voltage source element in my circuit, multiply it by my unknown node potential vector, and I get the vector of voltage source values on the right-hand side. Well, in matrix form, that thing looks like A sub Vg, the voltage source subblock of my incidence matrix, times the unknown and desired node potential vector is equal to the known constant, the engineered constant, the voltage drops across each of my voltage sources. That thing is determined by the original design of my circuit. This is where a linear algebraist might start licking her chops and saying, oh my God, I'm about to sit down for a nice meal. This structure is actually very, very famous in linear algebra. We have a left-hand side modeling matrix that is given. We have a right-hand side vector that is given. This matrix happens to be short and wide. We want to know what are all possible vectors that I can multiply by the given matrix to produce the given right-hand side vector. That is a canonical example of something called a general linear systems problem. But general linear systems problems are to linear algebra what Drake is to current hip-hop. They're very well known amongst math heads. Specifically, we have a famous theorem in linear algebra that says the complete solution to any general linear systems problem takes the form. So if I'm looking for the type of vector that solves this problem, that vector is always going to be in the form a particular solution to our system plus any trivial solution to our system. Now, if it's been a while since you saw that theory, or you want a refresher, I want to say I have a nice YouTube playlist on this. If you go to my website, appliedlinearalgebra.com, go over to blog, scroll down to classes and go to my linear algebra class. That's a Math 2B at Foothill College. And then if you scroll down all the way to the Lesson 18 playlist and click on that, you'll see a YouTube playlist that's designed, here it is, it has 10 videos, that's designed to give you a lot more intuition about how this theorem takes form, including a number of proofs that are directly relevant to that. But for a short recap, the claim is, if I want to analyze this linear systems that arise from thinking about how the voltage sources are connected in my circuit, I need information about something called a particular solution and something called a homogeneous solution. But the homogeneous solution associated with our original general linear systems problem, A sub Vg times Ug equals V sub V, if I want to define a homogeneous solution, what I do is I set the right-hand side equal to 0. That's the definition of what a homogeneous system is. In other words, I deactivate the circuit. This is where the deactivation heuristic comes in. If we're trying to get information about how the entries of our potential vector are related, I need information about a particular solution plus a homogeneous solution. But to find information about homogeneous solutions, I'm going to set the right-hand side vector to 0. In other words, I'm going to deactivate my circuit. I'm going to assume each of my voltage source values has value 0. That is the deactivation heuristic. Now, before we dive too deeply into what's going on with the homogeneous linear system, let me just give a general reminder. The point is, we have this connectivity of voltage sources. In that connectivity, there are redundancies within the individual entries of the vector u sub g. When we analyze this system with a known right-hand side, we can actually decompose the values of u sub g as a linear combination of something called a particular solution and any trivial solution to the homogeneous linear system. Particular solutions come in the form P sub g. In other words, if I multiply the particular solution by the original matrix, I get back to the right-hand side vector. The reason we call this a particular solution is because this vector solves the original problem with respect to the actual values of the voltage sources. In other words, the particular solution is related to the particular choice of voltage sources. It is very much dependent on how we define those sources in our problem. On the other hand, when I'm looking for trivial solutions, solutions that send the matrix A sub Vg to 0, that does not depend on my chosen values of the voltage sources in my circuit. But the fact that the voltage source information forms a general linear systems problem, and every general linear systems problem has a template that solutions follow, means that the vector u sub g that arises when trying to solve this problem actually encodes two different types of information. It encodes what we call particular information and then information about the homogeneous linear system associated with that original problem. But I would say that in a little bit more specific form. U sub g encodes information in two types. The first type of information has to do with interdependencies between the entries of that vector that result from the particular choice of the voltage source values. I would call that dependent node information. If I know one of them, then I get the other one for free as long as I know the entries of my voltage sources. The other type of information that is independent of the voltage source values would relate to the topology of the deactivated circuit where I've set V sub V to 0, where I've literally deactivated all of my sources. And that's exactly what's happening here in the structure of the template for complete solutions to my general linear systems problem. It's not a coincidence that step 6 is asking us to capture information about generalized nodes and ordinary nodes, and that when we look at the solution to our general linear systems problems, we have stuff that's particular solutions, giving us information about interdependencies of the individual variables within that vector, and then we have some other information about connectivity once we've deactivated the circuit. Now, the claim is these two types of information don't really map exactly onto these two types of nodes. In fact, there are some cross-pollination. We're going to get into that. But the point of the matter is the structure of these solutions actually gives us information about our circuit. In later videos, we're going to explore more about what the particular solution looks like and where it comes from. But for now, in the extension to step 6, I really want to focus in on trivial solutions. Specifically, we say that any trivial solution associated with the homogeneous linear system problem, when we multiply that trivial solution by our matrix, we get 0. In other words, any trivial solution solves the deactivated circuit problem no matter what choice of V sub V vector that I impose. Well, this relates to our original question, what's going on with the deactivation circuit heuristic? When we deactivate our circuit, we can highlight and explore the information having to do with independent node voltages that do not rely on our particular choices for values of our voltage sources. So the deactivation allows us to focus on information that is captured in the deactivated circuit topology, irrespective of the actual values in the voltage source vector. But once we come to that realization, we might want to really focus in on the homogeneous linear system arising from that voltage source subblock of the larger entire incidence matrix. And when we look at that homogeneous linear systems problem, there is another theorem in linear algebra that says that we can write any trivial solution to that problem as a linear combination of linearly independent special trivial solutions to this problem. If you want more on that, please see that previously mentioned YouTube playlist. There's a lot of information in that. But the point of the matter is, if I want to solve this general problem trying to send the matrix A sub Vg to 0, what I'm going to do is look for specific vectors that send that matrix to 0. We said that the number of linearly independent vectors that do that is equal to the number of non-pivot columns of that matrix, which in the notation I choose to use, I call lowercase f. Remember that the number of rows of the matrix A sub Vg is equal to the number of voltage sources. The number of columns is equal to the number of nodes in my original circuit. Those of you that have a lot of linear algebraic knowledge just sitting in the top of your head, you'll remember that if we say that a matrix has a certain number of columns, we can define something called the rank of a matrix, which is the number of pivots in that matrix, or the number of linearly independent columns. That's also equal to the number of linear independent rows, which is also equal to the number of pivot rows. More about that can be seen in the playlist that I've already linked to. But the number f, the number of special trivial solutions that are linearly independent, is going to be the number of columns minus the number of pivots. In other words, each column of that matrix is either a pivot column or a non-pivot column. Thus, if we want to find any trivial solution, what we're really going to try to do is to find f linearly independent solutions to this homogeneous linear systems problem, where f is the number of non-pivot columns of that matrix. But the moment we realize that, as linear algebraists, we might start salivating. The voltage source subblock of our incidence matrix given by this has really special form. For this circuit, it is actually written right here. This matrix is already in RREF form, which is the traditional technique that we use to find where the pivot and non-pivot columns are. In this case, we have one pivot column in column 2 and a second pivot column in column 4. Every other column of that matrix is a non-pivot column. Go back and watch previous videos if you want to see more about that information. Not only is this matrix super beautiful in this example, but in the general case, when I'm analyzing any circuit, these voltage source subblock matrices are actually really special. They come from the entry by entry definition of the incidence matrix A sub G associated with the digraph model of our circuit. Go back and watch step 3 of this algorithm if you want more specifics about that. But in step 3 of this algorithm, we recall that the individual coefficients of the entire incidence matrix are determined by the interconnectivity between the edges and nodes in my circuit. So if I wanted to find the jkth entry of my incidence matrix, I say that entry is 1 if edge E sub j leaves node k, it goes out of the node k, -1 if edge E sub j enters node k, and 0 otherwise. But remember, the whole point of this is to try to figure out how many different linearly independent special trivial solutions I have to the homogeneous linear system problem involving that matrix. I actually can say a lot about the rank of my A sub Vg matrix by looking at the structure that results from this definition. The first thing that I would say is that the individual rows of this subblock correspond to the edges of my digraph model that came from voltage sources. Another way to say that is if I want to know what's going on with those rows, I look at those two elements. Those two elements were modeled as directed edges from that node to that node, that's that voltage source, and then from node 4 to node 5, that's that voltage source. When I look at this matrix, the information about connectivity is encoded in each of those rows. Not only that, but every row is going to have only 2 non-zero entries. Those non-zero entries are going to be +1 and -1 based on the definition of that incidence matrix. The value that has a positive 1 corresponds with a column of the matrix, which is mapped back to a node to which the positive lead of my voltage source is connected. Check that out. The positive lead of voltage source 1 is connected to node 2. That value, the positive 1 value, is in column 2 of my matrix. The negative lead of voltage source 1 is connected to node 7. The negative 1 value is in column 7. Similarly, for voltage source 2, aka row 2 of this matrix, the positive lead of that voltage source is connected to node 4. Check that out. Positive 1 in column 4. The negative lead is connected to node 5. Negative 1 in column 5. So, each row of this thing is really special in the sense that it only has 2 non-zero entries. Every other entry in an individual row is 0. But the special structure of the matrix A sub Vg has immediate implications for measuring the number of linearly independent rows, the number of pivots in that matrix. And that is correlated with the connectivity of the original circuit. More specifically, I'm going to state a conjecture. I'm not going to offer a proof. I'll show you an outline of that. I kind of leave that as a challenge to my viewers. But the claim is, as long as there's no path of voltage sources that is parallel to a different path of voltage sources in our circuit, the rows of that voltage source subblock of our incidence matrix will always be linearly independent. Another way to say that is, if I want to know the rank of that matrix, that rank will always be equal to the number of voltage sources, assuming, of course, I don't have parallel voltage sources in my circuit. You might wonder, what do I mean by parallel voltage sources? These 3 voltage sources, there's a path of voltage sources over here that is parallel to this path of voltage sources over here. When I look at the graph encoding that information, that graph says I actually can move along these 2 edges and I get to the same information as I do if I move along this edge. When I look at the corresponding incidence matrix, check it out. This incidence matrix only has 2 linearly independent rows. In fact, if I add rows 1 and 2, I get to row 3. In other words, row 3 is redundant information with respect to rows 1 and 2. That's because what's happening in this voltage source is actually replicated what's happening with this path of voltage sources. But paths of parallel voltage sources are actually not realistic in electrical engineering design based on the functionality of voltage sources themselves. And what that means is, in any functional circuit that is actually useful, the rows of that subblock will always be linearly independent. But remember, the whole idea that we were trying to figure out is, what do trivial solutions to the homogeneous linear system involving that matrix look like? The moment that we know that the rank of that matrix is equal to the number of rows, in other words, every row is linearly independent, we can calculate the number of special trivial solutions to the homogeneous linear system as the difference between the number of columns and the rank of our matrix, which happens to be the number of rows. So that means that if I want to find how many solutions I should be searching for, it's going to be the number of columns minus the number of rows. But looking at this specific example, we see that there are 2 rows and 7 columns. I'm going to be searching for 7 minus 2, which is 5 linearly independent solutions. However, linearly independent solutions involving this matrix to the homogeneous linear system problem literally has to do with finding linearly independent column combinations that send this to 0. The structure of this matrix is really, really interesting. There are only 2 ways to send that matrix to 0 based on the fact that every row contains only 2 non-zero entries. The first way to send this matrix to 0 that is kind of unique is to combine columns that have 1s and -1s. So look for any column with at least 1 non-zero entry. Find another set of columns with non-zero entries. Look for linear combinations of those sets of columns that send the matrix to 0. That's one type of information. In this case, we see that if I add column 2 to column 7, generalized node, column 2 and column 7, that would send the entire matrix to 0. Also, if I added column 4 to column 5, that would send the matrix to 0. Ding, 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 ding. Generalized node, that's more information. The other way to send this matrix to 0 is to focus on the 0 columns. And in fact, check this out. Column 1 is all 0. So if I just multiplied by column 1, I would go to 0. Column 3 is all zeros, and column 6 are all zeros. Well, ding, 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 ding. Check this out. 1, 3, and 6. That's what's happening with our ordinary nodes. Let's get even more specific. Let's find the type of special trivial solutions that correlate with generalized nodes, and we'll start with generalized node 1. If we want to send this entire matrix to 0, I don't need any of column 1. Column 2, I need 1. 3, 0, 4, 0, 5, 0, 6, 0, 7, 1, I put a 1 in position 2 and a 1 in position 7. That's exactly what my generalized node 1 told me to do. If I wanted to find the second type in that category, I would put a 1 in position 4 and a 1 in position 5. Everything else goes to 0. Go ahead and multiply that matrix by either of those vectors and notice that they will take linear combinations of the non-zero columns that get sent to 0. The other type of special trivial solution, the one corresponding to ordinary nodes, literally what I'm going to do is I'm going to put a 1 in the position of the 0 column. So the first 0 column of that thing happens in column 1. The second 0 column happens in column 3. And the third 0 column happens in column 6. Now I have 1, 2, 3, 4, 5 separate solutions that send that matrix to 0. By inspection, we can tell that those are linearly independent, and we've broken each of those special solutions into categories, either special solutions that come from generalized nodes or special solutions that come from ordinary nodes. But that means when I'm going to solve the system A sub Vg times Z equals 0, the homogeneous linear system problem, I can actually completely categorize any trivial solution as a linear combination of my special trivial solutions, the 5 vectors or the F vectors that we just found by looking at the structure of that matrix. I always like to say to my students, this linear combination can always be written as a set of columns multiplied by a single vector. That's the column partition version of matrix multiplication, which means any trivial solution is going to be the matrix Z, whose columns come from looking at the linearly independent special trivial solutions, multiplied by some scalar vector C, where the scalars are chosen arbitrarily. With that in mind, the deactivation heuristic allowed me to set that right-hand side vector to 0, and then identifying the ordinary and generalized nodes really give me some very, very special information about what any trivial solution to the homogeneous linear system should look like. But this has real meaning when we think about eliminating unknown variables to get down to like this optimal set, this minimal set of variables that allowed me to solve for all other circuit variables in my entire network. While we've gone super deep just now, sadly, this analysis is not over. In fact, there are still some questions that arise. We have 5 vectors, but we haven't talked about enumerating the vectors, choosing Z1, Z2, Z3, Z4, Z5, or another way, how do we actually order the columns of these things, and does it matter? As a follow-up to this video, we're actually going to do a second extension, a second video on part 6, just talking about how the deactivation circuit heuristic and special trivial solutions relate to the larger structure of my circuit and allow me to reduce the dimensions of the unknown variables in my problem. I'll see you in the next video.